Hey there, welcome back to another math video with the Math Doc. We're continuing on the journey with absolute values and inequalities. And in this video, we will focus on trying to understand or interpret what the absolute value and inequality means. In a previous video, which I will link below in the description, we discussed how to solve inequalities that have variables with absolute values, so variables that are inside absolute values. Here, we're going to do in order to interpret this, we're going to go backwards. What we will do is we'll start with a double inequality or a compound inequality like you see right here. X is larger than -2 and x is less than 2. And I will link below also the videos that discuss compound and or inequalities. So we'll start with this and we'll build an absolute value inequality. And I think that will help with the interpretation and understanding what these inequalities actually mean. So let's look at what we have here. We have x is larger than -2 and x is less than 2. And I'm going to start here immediately with a number line. So right here is 0. We have 1, 2, 3, 4 to the right, -1, -2, -3, and -4 to the left. And what we have is x is larger than -2. So I'll do that and say in green, an open circle because it's larger than, not larger or equal to. And for any x larger than -2, we solve this first inequality. Now, the second inequality will be x is less than 2, and again, open circle, and I'm doing this one in red. So for any x less than 2, we solve this second inequality. Now, we have this end here, and as a reminder, when we have an end compound inequality, both inequalities have to be solved simultaneously. And that is the area where we have this overlap of red and green. So right here, or I will put it in blue on top. So it's this area. Now this area here, this interval between -2 and 2, is the interval of all the x's here, right, that are smaller than 2 or larger than -2. But their size, right, that we measure with the absolute value, their size is less than 2. So these two inequalities can be combined together to the absolute value is less than 2. So you see, this is sort of an interpretation of what we have here. We have a compound inequality with two inequalities that end up with this single absolute value inequality. Let's look at the opposite example now. In this example, we have x is less than -2 or x is larger than -2. So again, let's get ourselves on the number line and see what it looks like. Okay, so we have 0 here, 1, 2, 3, 4, and to the left, -1, -2, -3, -4. Okay, so now we have x is less than -2. Again, let's use our green here. X is less than -2 here. And in red, let's do x is larger than +2. And in this case, we have an OR compound. When we have an OR compound, it means that we have to include the solutions of both inequalities. So we have this area here and this area here, right? Because it's an OR inequality, compound inequality. Either one can be solved for a solution of both. Okay, so now we're looking at all the x's that are larger than 2 or less than -2. Again, if we look just at the size of x by using the absolute value, we're looking at x's that are larger than 2, or their absolute value here on this area is also larger than 2, right? They are negative, but the absolute value is larger than 2. So again here, we took a compound inequality and turned it into a single absolute value inequality. Now, what made these two examples relatively simple is that they were centered around the 0. Okay, we have here our 0 on the number line, and the inequalities are basically symmetric around 0. We have to take a step up and look at what happens when we have a non-symmetric case. So in this problem here, we are not centered around 0. Let's look at this on the number line again. We're in red, so let's make our 0 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's take a little extra. 12. Okay, so we have here, let's change color. We have x is larger than 6. Okay, here's 6, so we take that to be larger than 6. And we have x is less than 10. Okay, so in this case, we're clearly not centered around 0. And so in order to make an absolute value inequality out of these two inequalities, we will have to take a little shift from 0. And I'll show you exactly how to do that. But first, let's see what our inequalities say. Well, our inequalities are saying that we have to look at the x's that are in the interval 6 to 10, right? And we want to write it as x somehow is less than something, right? So the question is if we can just take the absolute value of x, and what is this question mark here? So let's look at this a little more carefully here. And let's see. So we have our numbers here, x are between 6 and 10. Let's count how many steps we have between 6 and 10. We have 1, 2, 3, 4 steps. Now, what is the middle of this interval? The middle of the interval would be 2 steps, right? If the entire interval is 4 steps, we will find the midpoint at 2 steps. So we're looking for the midpoint here, which would be at 8, right? 2 steps to 8, and another 2 steps from 8 to 10. So our midpoint in this interval is at 8. Okay, so we can guess that our interval will be, our absolute value will be centered around 8. Okay, now we said that the midpoint is at 8, but the number of steps we take to our midpoint is 2, right? It's 8 minus 6 or 10 minus 8. Either way, we get to that midpoint in 2 steps. So that means that our absolute value here has to be less than 2. Okay, so in this way, by finding the midpoint and by finding the size of the interval and halving it, okay, so we took the size of the interval, which was 4 steps, and we halved it, we could reach our the size of the absolute value has to be smaller than. Let's try to write this out now on a new number line. X minus 8 is less than 2. So we go to 8 here. Let's say 0 is here. And we go 1, 2, 1, 2. So this is 6 and this is 10. And now centered around X, we can go 2 to the right or 2 to the left. And our result is that X is either larger, it has to be larger than 6 and less than 10, which is exactly the result we started with. We will look at the opposite example in the next slide as well, and then we will do a couple of good examples. Now, when we look at the opposite case, again, let's look at it on the number line. We'll start at 6, 7, 8, 9, 10, and we'll take a few extra numbers from both sides here. And we have x is less than 6, right? Or x is larger than 10. So we're actually looking at these two intervals, right? We're looking at the interval negative infinity to 6 or the interval 10 to positive infinity. And so in this case, we expect to get some kind of absolute value of x minus something is larger than something, right? And we will figure out what these somethings are, but we know we have a larger than because in this case we're going away from our midpoint here of 8. So we're looking at a larger than, at numbers that have a size that is larger than some constant. Okay, again, we're going to look for the midpoint. And again, what is our midpoint? Well, our interval is, again, 1, 2, 3, 4 steps, right? Interval of 4. So our midpoint will be at 2 steps in. 1, 2, that is 8. 8 is our midpoint. And half of our interval is just 2, right? So our new absolute value inequality is x minus 8, right, is larger in this case than 2. Okay, let's look at that on a new number line. We have our midpoint at 8, and we're looking at x's that are either larger than 8 by 2, so they start at 10 here, or less than 8, but their distance from 8 has to still be larger than 2. So we're looking at starting from 6 and going down to negative infinity. So again, we took this compound inequality, we turned it into an absolute value inequality, and that both satisfy the same conditions. The solutions for both are the same x's. Now we're going to move on to a couple of word problems that will help us understand this even better. So let's get started on the first word problem. So a healthy person's body temperature in Celsius is less or equal to 37.6 degrees and above or equal to 36.4. Okay, write this condition as an absolute value inequality. Okay, what I like about this problem is that it's transitioning us from whole numbers to decimals, and it'll show you how to do this without counting steps between the numbers. So let's get started. We can still draw this on a number line so that we get a feel for what we're looking at. So if we have body temperature somewhere between 36 and 38 degrees, let's draw that. Let's say 36 here and 38 here and 37 degrees Celsius here. This is all in Celsius, not Fahrenheit. And we say that it is above or equal to 36.4. Let's 6, 7, 8, 9. So 36.4 is right here. And it's less or equal to 37.6. 6, 7, 8, 9. Okay, 1, 2, 3, 4, 5, 6 is there. Okay, so basically we're saying anywhere between 36.4 and 37.6. Okay, so this is the area, right, where a healthy body should be. Anything above that is 6. is sick, right? Let's write that here, sick, and I don't know what under temperature would be, but let's just say cold. Okay, so we're looking to turn this into an absolute value problem. And how do we do that? Well, remember, we're going to look for the size of the interval. We will look for the midpoint. And we will also look for half size of interval, right? That'll help us build the inequality. So starting with the size of the interval is given by the difference between the two numbers, right? And we will take the large number, 37.6, and subtract the lower number, 36.4, and that'll give us the size of the interval. This is also true if one of these numbers is negative. If we had a negative number, we would still subtract, but remember, when you subtract negative, the two negatives cancel and you actually end up adding the two numbers. And we will see an example like that. But let's start with this. So we have 37.6. I'm going to do that right here. Minus 36.4. We have 2 behind the decimal point, 1, and these two numbers cancel, the 2 3s. So we have, this is just 1.2. Okay, what is half the size of the interval? Well, 1.2 divided by 2 is just 0.6, right? Okay, so the half of the interval is 0.6. And so now we're getting to the midpoint. What is the midpoint? Well, the midpoint is either 36.4 plus 0.6 or 37.6 minus 0.6. And if we did our first calculations correctly, these should be equal. So 36.4 plus 0.6. 6 plus 4 is 10, so we get a 0 here plus a carryover, that's 7, and we get 37, right? That's our midpoint. Let's just check that the other set of numbers gives us the same result, 37.6 minus 0.6. 6 minus 6 is 0, and we get 37. So great, our midpoint is just 37. And I will outline all our numbers here. Let's do that with a different color. 37 is our midpoint, our interval is 1.6, and half our interval is 0.6. Okay, so now let's write our absolute value. Let's use T. Let's use T as the body temperature. Okay, that is our variable. So T minus our midpoint. What is our midpoint? It's 37. Absolute value is less or equal to the half of our interval, which is 0.6. So this is the result we were looking for. This is the same problem, the same conditions as we had here as a set of two inequalities with a single absolute value inequality, and you can take the time to check this again to show it on a number line, right? We have 37, we can go 0.6 up, 37.6, we can go 0.6 down, 36.4, and we're within this region, this healthy region. So let's look at another temperature problem, but this one we'll add the complication of a negative lower limit so that we can practice that as well. So here we're not looking at the temperature of a human, but of a car engine. So according to this problem, a car engine will operate fine as long as its temperature is lower than about 104 degrees Celsius. Let's put that here, 104. On the other hand, we know that gasoline will start freezing at about negative 40 degrees. Let's put our 0 here and our negative 40 here. So the gasoline will freeze under negative 40, so obviously the car won't run there. And so we're looking at this an inequality, a set of inequalities where the temperature T has to be larger than negative 40 and less than 104 here, right? So if it gets over 104, gets too hot, we'll write that in red. And if we get below negative 40, it'll freeze, right? The gasoline will freeze. So the problem here is that we would like to write an absolute value inequality that describes the required operational temperature for an engine. Okay, so what do we have here? Again, we have to look for the size of the interval. The operational interval, we will look for the midpoint by finding half the size of interval, right? So we'll need that, and then we'll get the midpoint. So here we are. So we have size of interval. Again, we take the larger number, 104, and subtract the lower one. The lower is negative 40, right? So we have 104 minus negative 40. Remember, we have two negatives, so that'll turn into an addition problem, negative, negative, and the entire interval is just 144. Okay, what is half of our interval? What is a half of 144? That's exactly 72, right? 140 divided by 2 is 70. Then we divide the 4 by 2, that's another 2. So we have 72 here. What is our midpoint? Well, let's start with negative 40 plus 72. Okay, that will be equal to plus 32, right? Let's also look at the other direction. Let's look at 104 minus 72. Let's do that over here. 104 minus 72. 4 minus 2 is 2. 0 minus 7 is impossible to do, so we'll borrow the 1, and we have 10. That's 32. So in both cases, we get our midpoint to be 32. Let's highlight all our results. Okay, so the midpoint is 32, and half of our interval is 72. The full interval is 144. And so if we want to write down our solution now, again, as an absolute value inequality problem, we have T minus our midpoint, which is 32 in absolute value, is less than half of our interval, which is just 72. So this is the result for the operational interval of a car engine. That is in degrees Celsius. Okay, we have one final problem coming up. And this example has nothing to do with temperature, not of cars and not of humans. We're looking at an airport problem where we have an airplane that leaves New York City with an expected travel time of 90 minutes. Let's underline that. It has booked a landing slot at its destination for 90 minutes later. In order to avoid congestion at the destination airport, it is allowed a margin of 15 minutes. It can be either 15 minutes early or late. Write an inequality for this constraint on the travel time. Okay, so the travel time will be, let's call X the travel time, right? That is our variable. And we know that optimally it should be 90 minutes. So that means that we're looking at an interval around 90 minutes, and the size of the interval Okay, from each side we have a margin of 15 minutes. Okay, let's draw this on the number line. So if this is the travel time, x, we have here 90, and we can go either minus 15 minutes or plus 15 minutes, right? So we can go to 105 or down to 75 minutes, depending, I guess, on wind and other variables in our flight time. Or now, how do we write this absolute value problem? Well, we have our midpoint, right? This is our midpoint. So we know that our problem is going to be x minus 90. And since we want it to be just an interval of 15 minutes between the actual landing time and our request for 90 minutes, then this has to be less or equal to 15, right? This is our absolute value problem. So this one is even simpler than our previous ones. How do we solve this inequality? Well, we basically solved it up here by looking at the number line. So we have the interval x should belong to the interval 75 to 105. And if we say that it's less or equal to, we actually want it to be the interval that includes the edges, so we'll use the square brackets. So this is the result, right? We're looking at the interval of 75 to 105 minutes travel time. Okay, so this brings to the end our last video on inequalities with absolute values. If you have any questions, please include those in the comments below. If you're new to my videos and you'd like to subscribe, please do so. I will be happy to answer any specific questions if they show up in the comments. Thanks and bye-bye.